This you can do it by the end of the semester. Correct. By the last class or the final exam you can do it. This all the 3 assignments, this 2 assignments, the computer assignment and the problem formulation, you turn it over at the end. Okay. So, now, so I think in the last class we looked at the calculation of the heat capacities. First we started off with the heat capacity of gas molecules. Okay. So, we used the Maxwell-Boltzmann distribution and we formulated it. Next we looked into the phonons. So, we used the Bose-Einstein distribution function, calculated the expression for the heat capacities. So, these are volumetric heat capacities. So, the units for this is joule per meter cube Kelvin, right. And in this case I think towards the end we hurried up, but I asked you to check. We have the expression for basically the heat capacity like this, and then we also have an expression for the number of quantum states per unit volume by integrating the density of states, and then we rewrote this expression in terms of n by v. So, we substituted for n by v and it looks like this. Why we are putting in this formulation is that here, as you can know, in the case of phonon crystal, so these n number of quantum states with n atoms. Okay. So, there are with n number of atoms you have n number of quantum states. So, therefore, these are nothing but number of atoms in the crystal structure. Okay. So, if you are therefore looking at a particular crystal structure, say monoatomic. So, these are again valid for only monoatomic ones with the acoustic phonons considered. So, we have the d by approximation. So, I hope all of you can recollect that. So, even this with now a chain of these atoms forming the crystal. So, if you know the count of these n number of atoms, therefore, that can be directly substituted to get the heat capacity, and this integral can be evaluated depending on the upper limit of the integration, which is your d by temperature, and the d by temperature we have defined here. It is an equivalent temperature equal to some kBT, similar to the temperature that we replace here with the d by temperature for the crystal, that is equal to h bar omega. Okay. So, this corresponds to actually omega d. So, this is your d by frequency which decides your d by temperature. So, once you know the value of d by temperature, we substitute this, calculate this integral, and we also will know at a given temperature what is the ratio of theta d by t. We will know number of atoms. So, therefore, we can evaluate what is the volumetric heat capacity. So, the final energy carrier for which we need to evaluate the heat capacity is the electron, right. Okay. Now, when it comes to electrons, phonons, it is clear, phonons in metals they do not play a very vital role. They are mostly in semiconductors or dielectrics, their contribution is significant, but electrons are like everywhere. They can be important in a semiconductor also and predominantly in metals. Okay. So, their contribution is there both in semiconductors, dielectrics and also metals. So, therefore, our analysis has to be slightly different when you look at metals and calculate the heat capacity compared to semiconductors. Why? Because of the dispersion curve. Okay. So, we will right now focus mainly on the metal structure, where if you recollect how your dispersion curve was. So, that is your E versus K. So, do you recollect? We have a conduction band approximated like this, correct. We could also have a valence band like this. and this was the band gap. And where is the Fermi level located? Usually in the case of metals, that is inside the conduction band. So, this is what is going to make the analysis different between metals and semiconductors, the location of the reference, the Fermi level. So, therefore, we start with the edge of the conduction band which is at reference 0 and from which we start our integration, correct. So, therefore, if you want to calculate the internal energy for the electrons, so again we will apply our rule that you have a distribution function for the electrons occupying each and every quantum state or energy level, right, and therefore, we multiply it with the corresponding energy of that quantum state. So, that is your electron energy E, that is the energy level of particular quantum state. So, this distribution function will be your Fermi Dirac, and the Fermi Dirac is a function of what? It is a function of the electron energy E, temperature and the chemical potential mu. So, for sometimes for reference sake we can take the chemical potential to be equal to the Fermi energy level EF. Okay. So, we know therefore, so F is nothing but your volumetric distribution of electrons. So, electrons occupying a particular quantum state per unit volume, okay, multiplied by the energy of that particular quantum state, and when you sum this over all the energy levels, that will give you the volumetric internal energy, right. So, based on this we can calculate your heat capacity. Okay. So, now what we are now going to do in this case, unlike the phonons where we did again, we use the summation over all the quantum states and then we converted this summation to continuous integral. The same way in this case we have a dispersion relation which is continuous, and so is our density of states d of E as a function of E. So, if you plot the density of states, okay, so it will start from 0 at the edge of the conduction band, right. So, and somewhere you have the Fermi level. Okay. So, you have E minus is a function of E minus E c, so on. So, therefore, to convert this into a continuous integral, again we resort to using the density of states. So, this summation, discrete summation will be replaced by a continuous integral by introducing the density of states. So, the density of states is nothing but the number of quantum states per unit volume, and if you multiply it by the energy gap dE. So, that is nothing but the number of quantum states per unit volume. So, therefore, this has to be multiplied by density of states dE. So, the discrete summation will now be replaced by a continuous integral, and the limits of this integration. Now, the density of states we have to go from 0, which is the starting of the conduction band, and the electrons can move all around anywhere within the conduction band. Okay. So, it can actually go up to infinity. Right. And if I want to calculate the number of electrons per unit volume or number density of electrons, within the conduction band, these are the free electrons. See, electrons are there right from valence band and even before. but why we are interested in only this band? This is what is contributing to the actual internal energy, because these are the free electrons which are actually moving about, transferring the energy from one end to the other. Okay. So, these are the ones which are free to move, these are the free electrons. So, therefore, we are interested in only accounting for the electrons in the conduction band. So, if you want to, therefore, whenever I say electrons, do not think that these are the only electrons in the entire crystal. So, these are the free electrons. So, number of electrons per unit volume, how do I calculate? So, I want all the free electrons in the conduction band. Again look at this, again look at this. If you remove E from here and just simply sum the distribution function, what does it give you? So, particular quantum state, these are the number of electrons per unit volume, next quantum state number of electrons. So, if you sum all this totally, it will give you the number of electrons per unit volume, right. So, therefore, how do you calculate now number of free electrons? Let us say n subscript t, this is the number density of free electrons. Replace sigma with integration. Integral 0 to infinity what should come inside? D of E dE, D of D E dE gives you only quantum states, it does not give you how many electrons are actually occupying that. F D of E, right. So, the actual number of electrons occupying each and every quantum state, you have to multiply by the distribution function, right. Now, for a given metal, for example, this number of free electrons is constant, correct. This value is a constant, it can move around, but this number is a constant, therefore, this is equal to a constant. So, next what I am going to do, let us say this is equation 1, this is equation 2. So, I am just going to do a little bit of manipulation with equation 1. So, I will add and subtract my Fermi energy level to this. So, I can write this as E minus E f, because Fermi energy level is a constant value, because this is the value of chemical potential at 0 Kelvin. See, or it tells me till what energy are the electrons occupying the conduction band at 0 Kelvin. Okay, that is my reference level. So, that is a constant value. So, I can simply add and subtract that. Mu d of E dE. So, plus now I have to add E f f E t mu d of E d, right. So, I hope you understand what Fermi level is, where Fermi level is the chemical potential at 0 Kelvin. Chemical potential means that is the potential up to which it is the energy level up to which the electrons are filling at 0 Kelvin. Okay. So, at different temperatures this level will be different. Of course, at higher temperatures this level will keep moving down and down, further down. So, that gives you the local chemical potential, that is your electrochemical potential people call it, right. So, but we are interested in the reference at 0 Kelvin. So, there that value is fixed, and therefore, now if you want to calculate the volumetric heat capacity of electrons, this is simply du by dt. So, therefore, what happens to this second term? This is 0. Okay. Why? F is a function of temperature. Correct. So, therefore, we have now defined Ne as integral this. So, therefore, this can be written as Ef into Ne, correct. Ef is a constant. So, therefore, Ne is a constant, Ef is a constant. The derivative of this will not change with respect to temperature. Okay. So, therefore, we will have, so what will change out of this first term with respect to temperature? Only the distribution function is a function of temperature. So, you have therefore, E minus Ef into df by dt d of E dE, right. So, can you calculate what is df by dt? You know your Fermi-Dirac distribution function 1 by exponential E minus mu by kBT plus 1, right. So, therefore, calculate df by dt. Derivative with respect to temperature. So, we have E minus mu, correct, upon kBT square, correct. So, E minus mu by kBT by plus 1 the whole square, right. Okay. So, therefore, your CE 0 to infinity E minus EF, we have E minus mu by kBT square into exponential minus mu is that fine? Okay. So, now we have to have the, that is why here we have to understand the how the density of states behaves, how the distribution function behaves. So, if you look at the Fermi-Dirac distribution function once again, right. So, if you plot your FFD as a function of E, okay, at 0 Kelvin how does it look? Huh?
Should not have like a minus symbol, like exponential of minus of E minus mu by kb. The function will have minus minus will be cancelled.
Minus minus should cancel, I think. In the df by dt you are saying, or
No, in a exponential of minus of E minus mu by kb.
this is 1 by this.
Right.
Yeah, so I don't think there will be, I don't think there should be another, is it? Just check. I think it's plus. I think it should be fine. So minus of E minus mu. Okay, let me just go back and check. Then how did I miss this? Oh, okay. I think I must have made this mistake in the beginning. Where did I make it? Because it should be just plus E minus mu by kBt. Let me check. But when we derived this, I think there was plus E minus mu. I think probably in the table I must have made this. Okay, but let us see if table we made this. Okay. Yeah, here we have plus E minus mu. Okay, so I think while we derived it, it was correct, but I think after that in the table I made the mistake. Okay, so it should be plus, please correct it. Okay, so that at very high energy levels it should go back to the Boltzmann distribution function, that is exponential minus E minus mu by kBt. Okay. So at 0 Kelvin, okay, if I know my Fermi level as this EF, at 0 Kelvin how will this distribution look? This is 0, this is 1. What's that? 0 where? At EF, okay. So therefore, how does it look?
It is symmetric about the curve is symmetric.
Yeah, symmetric is, it will be anti-symmetric. So it will be a step function, right? So everything below the Fermi energy level is occupied. Above a Fermi energy level there are no electrons, because why? At 0 Kelvin the maximum till which energy level till electrons are occupying is the Fermi level. Therefore, if you take Fermi level as the reference, at 0 Kelvin you have only electrons occupying till the Fermi level. So therefore, the occupancy function is 1 up to the Fermi level, above which there are no electrons, completely 0. So slowly at higher temperatures this will start shifting from this Dirac delta function to a more continuous function. So this then slowly it will become like this at maybe 100 Kelvin. At even higher temperature it will become more gradual, and then finally very high temperature it will be just some straight line like this, correct. So what does it mean? So at higher and higher temperatures the electrons can move conduction band more freely. So therefore, there is a good amount of chance that also the lower energy levels and the energy levels beyond the Fermi levels are also occupied, correct. You are understanding? If you look at again, you go back to the dispersion curve here. Okay. So, if you are talking about 0 Kelvin, so you have electrons occupying till here, above which you do not have anything. Now, as you keep raising the temperature, the electrons can keep moving this way, and therefore, there will be some possibility that electrons can fill all these higher states. So, very high temperatures, you will have lot of electrons filling also the higher states, it can freely move about, and therefore, you will slowly see the shift from a sharp cutoff like this at 0 Kelvin to more smoother and finally nearly a straight line. That means, you have equal probability of electrons occupying above Fermi level and below Fermi level. So, therefore, if you look at the gradient df by dt, right. So, df by dt is this particular value will be typically non-zero only around this center, that is about the Fermi level. So, this region and this region. Okay. So, if you look at df by dt in regions which are typically close to the lower energy levels and higher energy levels, they will not change much, but primarily the maximum change will happen about the Fermi level. The gradient df by dt will be mostly about this value, and therefore, and about this value, what happens to the density of states? It will usually taper off. So, we can assume that where the df by dt is maximum, that is around the Fermi level, your density of states is nearly a constant. Okay. So, with this assumption, we can therefore pull this density of states outside the integral. Okay. So, therefore, we can rewrite this equation as d of Ef. So, we will assume that this density of states is not going to change too much from your Fermi, the value at the Fermi level. The Fermi level already reaches somewhere close to the saturation point. So, now the next d of mu might be somewhere here, the next d of mu might be somewhere here, but all these values are negligible change compared to d of Ef. So, therefore, we will assume that that is constant equal to d of Ef. So, that we will pull this outside directly the integral, and therefore, this integral now will become important only in a region about Ef. So, therefore, we can write this 0 to infinity now as Ef minus some d Ef, Ef plus d Ef, that is we take a band about this Fermi level about which we are now doing this integral, because that is where df by dt is primarily non-zero, the other places it will be negligible. Okay. So, therefore, we can write about this zone, we can replace this E minus mu with E minus Ef. Okay. So, therefore, we have E minus Ef the whole square by kb t square into exponential E minus Ef by kb t divided by exponential E minus Ef by kb t plus 1 the whole square d. So, we can assume some dummy variable x is equal to E minus Ef by kb t. So, therefore, this can be written as kb square, some rewriting into t times d of Ef integral So, my 0 to infinity for example can be replaced with, if I replace E with dE with dx as the dummy variable. Okay. So, this will become x square e power x by e power x plus 1 the whole square. Okay. Please check this, therefore, I will have an additional kb square in the numerator and t, right. So, I am replacing dE as dx times kb t, right. So, the lower limit, so the original integration was from now 0 to infinity. So, therefore, E equal to 0 means x equal to minus E f by k b t. So, that is your modified lower limit, and E equal to infinity means x equal to infinity.
So we have already one kbt square is there, so we have to only multiply and divide with kb.
kbt, yeah, that is a kbt square.
kb.
Yeah, so therefore, we have to multiply and divide by again kb, so that this will be x square,
Yeah,
and therefore, we have a kb square. From dE also we have a kb, and then we multiply and divide by kb. So, you have a kb square outside. Okay. So, kb square t def, and this becomes x square. Is it okay? So, this particular integral turns out to be this particular integral turns out to be, if you evaluate, equal to a constant pi square by 3. Okay. So, therefore, your and also we can substitute for so one more thing, what we may have to do is the number of electrons. So, we have written down the expression for calculating the number of electrons, right, that is your equation 2. So, therefore, if you substitute for the Fermi-Dirac distribution function, so 0 to infinity f d of E dE. So, if you substitute for f and then also the density of states. Okay. So, I will just give you only the final expression that comes out will be 2 by 3 E f d of E f. So, this is your number density of electrons expression. You can actually just try it out as a homework, substitute for f and d of E, and then you evaluate this at 0 Kelvin. Okay. So, that means you will be integrating only till the Fermi energy level E f. Okay. So, therefore, you can rewrite our expression for heat capacity. You can replace dEf in terms of Ne and Ef, and therefore, your C turns out to be 1 by 2 pi square Ne kb into T by Tf. Where Tf is equal to Ef by Kb. So, this is another temperature, this is called the Fermi temperature. Just like we have the Debye temperature in phonons, we are defining, introducing, these are not physical temperatures. Okay. some kind of conceptual temperature based on the value of the Fermi energy level, similar to the Debye temperature which is based on the phonon energy level at omega d. The same way we are now introducing another temperature and we are substituting for EF in terms of TF as Kb times Tf, and therefore, this is our final expression, let us say 3. So, therefore, according to this expression, once you know the number density of electrons, free electrons, you know the Fermi temperature based on the value of the Fermi energy level for that metal and the actual temperature, room temperature or elevated temperature, you can calculate the heat capacity. So, and therefore, if you plot it, how does it look with respect to temperature? So, we have heat capacity, volumetric heat capacity joule per meter cube Kelvin, and we have a log scale in the temperature 1, 10, 100, 1000. How does it look for the case of electrons? This is a constant, this is a constant, this is a constant for a given metal. So, it will be a straight line, right. So, it will start from some value at 1 Kelvin and then go up like this, right. Whereas, for phonons we have our expression which is given by this. Once you know the number of atoms per unit volume, you know the Debye temperature, substitute this and we can plot this as a function of temperature. So, how does it look if you plot it? It will be like this, it will go on and then finally it will saturate. Okay. So, this is for phonons. So, in fact, for the two limits for phonons, I have not actually discussed this. So, let me quickly complete that. For the case of very low temperatures, so that is one end. So, that is the case where theta d by T going to low temperature limit, infinity, very small values of T, maybe order of 1 Kelvin, 2 Kelvin, cryogenic temperatures. Okay. So, theta d by T going to infinity, then Cv will actually go as, if you evaluate it, cubic power of temperature. Okay. Whereas, for the other case where your T is very large, theta by T going to 0, if you evaluate Cv, this turns out to be a constant equivalent to 9 n by V Kb. So, this integral will exactly turn out to be theta d by T the whole cube. So, this will cancel off and then you will exactly have a constant value. This is for the high temperature limit and this is for the low temperature limit. So, therefore, at the low temperature case, your heat capacity, if you look at really zoom in, this will be a cubic variation of temperature here, it will be like this, it will not be a straight line. So, this is your Cv going as T cube. Okay. And for the high temperature case, this will be a constant, right, and in between you have some kind of a linear variation. So, this is the nature of the heat capacity variation for phonons and electrons. Okay. So, we will stop here. So, I think now you must have a good understanding of what statistical thermodynamics can tell us. So, it has helped us to define internal energy from all the microstates, based on which we can calculate a very important property of the material, which is the heat capacity. And depending on whether we are dealing with gas molecules, whether we are dealing with semiconductors, dielectrics, or with metals, we know how to evaluate heat capacity, what is the contribution to heat capacity in each case, and how it behaves with temperature. So, the next problem is to look at the transport of heat. So, if you want to solve the diffusion equation, so one parameter, one property is heat capacity, which we have obtained from this, the other is your thermal conductivity. So, thermal conductivity we cannot obtain from just assumption of equilibrium, because it is a transport property. So, we have to look at transport of heat by the energy carriers. Only under that situation we can evaluate the second most important thermophysical property. So, once you understand how to evaluate that, then we can directly evaluate the thermophysical properties from a very fundamental understanding and solve the macro scale equations. So, the next class we will start with a hand waving argument of evaluating your thermal conductivity for heat conduction, and in the case of hydrodynamics, viscosity. Okay, that is your transport property, that is also a physical property, right. So, these two will evaluate in a hand waving argument using what we call kinetic theory, before we go to the rigorous method using the Boltzmann transport equation. Okay. So, this class completes the equilibrium, the so called equilibrium part. So, the statistical thermodynamics can only give this much of information, but if you want to go calculate the transport properties such as conductivity, viscosity, and so on, then we have to look into also the transport of heat, flow, and so on. Okay. So, tomorrow's the next class we will start looking at evaluating these other thermophysical properties also. Okay.
What is the limit of the integration CV?
For which case?
This finite electrical electron.
The electron case, I think this,
E minus EF case.
yeah, this one, right. So, it goes from minus EF by kBT to infinity. This turns out to be a constant, that means the value of EF is kind of frozen here. So, this should be a constant, the lower limit.
So, it will put E as a EF minus DEF, then it will gives like minus DF upon kBT to plus DF or something. It will be that minus EF upon kBT.
I mean, the reason why I have involved that is to only tell you that dE can be pulled outside the integral. Okay. You can actually do the integration from 0 to infinity, but I wanted to pull dEF outside the integral by telling you that dF by dt is very strong gradient only about the EF, about which your density of states is invariant. So, I involved that approximation to pull dEF, but you can actually do the integral right from 0 to infinity. So, therefore, your integral will in this case, after you transform it to a dummy variable, it will be minus EF by kBT to infinity. Is that okay? What was your question? That was your question, right? We were actually looking at EF minus DEF.
That value in the dummy variable, I didn't get that value. That's why I asked.
Oh yeah, so that is at E is equal to 0. At E equal to 0, x equal to minus kf by EF by kBT, and at E equal to infinity, it is infinity. Okay. All right. So, we will stop here.